Okay, what we're going to do now is we are going to practice doing electron configurations. I've picked out a few elements from all areas in the periodic table, and that should give us enough background to get a handle on this. Initially, this is going to feel or seem complicated. It's actually not that bad, and so if you'll just stick with it, pay attention, I think we'll get through this fairly well. So first of all, here are the components of the periodic table and the way you need to remember them in order to do electron configurations. Over here with the alkali metals and the alkaline earth metals, they all constitute the S block. And what that means is that these elements, their valence shell electrons are in the L equals 0, which we call the S subshell. So all of these, their outer shell electrons are in the S subshell. Over here on this side, we've got the L equals 1. That's the P block. So all these elements that are sort of outlined in the orange, they represent elements whose outer shell electrons or valence electrons are in the P subshell. We just know it as the P block. Here we have the D block. These are the transition metals. And that's L equals 2. That equals D. This is the D block, and we'll do some electron configurations for elements in the D block. And then this is the F block. Probably not going to do much with the F block in this particular course, but I will at least introduce elements in the F block. Okay, so this is what you need to remember in order to do electron configuration. Okay, so what we're going to do now is we're going to practice writing electron configurations for several different elements that I've highlighted. The first thing we'll do is we'll go ahead and do lithium. And for lithium's electron configuration, here's lithium. Remember, we want to fill up those lowest energy orbitals first. That's actually called the Aufbau principle. So we're going to start out filling out the 1s electron. So that's going to be 1s, 2. Then we've got, there are no p electrons for lithium. So we're going to come on down to the 2s. And there's one electron there, the 2s1 electron. So 1s, you can only put 2 electrons into the 1s, and then you have to drop down to the 2s. All right, so let's go ahead and do carbon now. So carbon, very important element. We're carbon-based life forms. Let's do carbon. We're going to fill up the 1s first because we fill the lowest energy orbitals first. Then we go down to n equals 2s. So we fill those up, 2s, and you can only put 2 electrons in an s subshell. And then finally, we get to the 2p. And you look over here and you see n equals 2, and this is the p block. Carbon is 2n, so that's going to be 2p2. And that is the full electron configuration for carbon. So electron configuration for carbon. All right, let's go ahead and let's move on down. What have we got next in the hopper? Let's do phosphorus. So here is phosphorus right here, atomic number 15. And we're going to go ahead. You've got a lot of phosphorus in you as well. So we're going to fill up those low energy orbitals, 1s2, 2s2, and then we're going to go all the way across and fill up the entire 2p subshell. Remember, you have to fill the lower energy orbitals first, and there's 6 electrons that you can put in any p subshell. 1, 2, 3, 4, 5, and 6. So that's 2p6. Then we drop down to n equals 3s, and we're going to do 3s2. So that's going to give us 3s2, and then we come over here to the 3p's, and there are 3 electrons in to get to phosphorus, so that's going to be 3 p3. And that describes the electron configuration for phosphorus. It is the full electron configuration. I'll show you a little bit of a shortcut in just a little bit. You could count up the electrons. There are 15 electrons in phosphorus, so that's 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15 electrons for phosphorus. All right, let's go all the way over here to argon, which is a noble gas. So let's go ahead and do argon. And so we have 1s, 2, 2s, 2, 2p6, 3s, 2, and then finally we're going to fill up the 3p's, so that'll be 3p6. And that is the full electron configuration for argon. All right, I'm going to introduce you to something that's a little bit of a shortcut in just a moment, but let's do calcium first. All right, so there's calcium. We have to drop down to the 4s, and so here's calcium's electron configuration. Let's do the full electron configuration. 1s, 2, 2s, 2, 2p6, 3s, 2, 3p6, and now we're dropping down to n equals 4. We have to go 2 over in the 4s subshell, and so 4s2, and that is the full electron configuration for calcium. Tell you what, let's go ahead and let's do one of the transition metals. We'll do titanium, which is right here. Now, here's something that is going to freak out a little bit. The 3Ds, before we start filling them up, are actually at a slightly lower energy than the 4s after we fill up the 4s and get to calcium. So we start filling these up. And so we do what we call backfill the Ds. And what that gives us, according to the rules of quantum mechanics, is that N, starting with the transition metals here, we go from N equals 4 to N equals 3. So it drops down. So this is actually, these actually start at 3D, and it goes 3D all the way across through zinc, and then you go back to the 4Ps in the P block. So this is going to be 4s and then 3D, and then we go to 4p. So let's go ahead and let's do, what did I have marked? Let's do titanium. So here's titanium, and we're going to do the full electron configuration, and then I'm going to show you something that will make your life a bit easier. So we fill them up from the bottom up. That's 1s2, 2s2, 2p6, 3s2, 3p6, 1s2, 2s2, 2p6, 3s2, 3p6, and then we go to 4s2 and then 3d, and we have to count over for titanium. That's 1, 2, so that gives us 3d2. Now, a couple of things. The 4s electrons are still the valence electrons. This is still the valence shell. Why is it the valence shell? Because it's the highest in value in this electron configuration. So it's the highest in principal quantum number. And the highest in principal quantum number, if you remember, in the quantum numbers, the n value tells you how far the electrons are away from the nucleus. So the highest n value, that's the outermost shell, that's the valence shell, that's where the electrons actually are lost or gained first. If it's a metal, it tends to lose electrons, and if it's a non-metal, it tends to gain electrons. So these are the valence electrons. So metals tend to lose electrons in chemical reactions. they tend to oxidize, and so these are the electrons that would leave first if titanium were to, for instance, go to titanium plus 2 cation. And we'll talk about that in a little bit. All right, so I want to introduce you to a different kind of notation. We call it core notation. First of all, take a look at argon's electron configuration. It's full electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. If I go down here to titanium and I look at 1s2, 2s2, 2p6, 3s2, 3p6, I look at that and I say, well, gosh, that's just the electron configuration for argon. Is there some kind of notation that I could substitute using the argon noble gas core? And the answer is yes, you can. You can use what we call core notation. That is, you take the noble gas electron configuration that's immediately above the element of interest, which in this case is titanium. And so this is simply going to be that notation. And so the rest is just 4s2, 3d2. And we call that core or condensed notation for an electron configuration. Notation. Okay, so let's do a couple of more. This time we're going to employ core notation just to get out of the necessity of having to write all the full electron configuration. So let's go ahead and let's do manganese. And we're going to use core notation for manganese. So here it is. What is the noble gas core that we'll use? We'll go ahead and we'll use argon's core. So that's going to be argon. And just keep in mind that argon core takes care of all of that. And then all that's left for manganese is 4s2 and 3d. Well, let's count them up. Let's go 1, 2, 3, 4, 5. That's 3d, 5. And so this is core notation for the electron configuration for manganese. Now, let's go ahead and remember and keep in mind that whenever you get to the transition metals, you go down from n equals 4 to n equals 3. And yes, this would be n equals 4 down here, n equals 5, and so on. Let's move down and let's do selenium, and I'll save copper and chromium for last. We'll do that on the next slide. So here is selenium. And we're going to use core notation. So again, we would use an argon core because it's the noble gas. It's above selenium. That's what we use. So that's going to be the argon core. And then we're going to come back. We're going to do 4s2. We have to fill up the entire 3D subshell, so that's going to be 3D 10. And you want to remember that a D subshell can hold a maximum of 10 electrons. And just remember that a D subshell can hold a maximum of 10 electrons. And then we go back to 4p, and selenium is 1, 2, 3, 4 over. So that's going to be 4p4. And that is the electron configuration using core notation for selenium. And we're just using the noble gas core. So if we're going to use core notation, let's say, to write the electron configuration for antimony, Sb down here, our noble gas core would be krypton. And if it were bismuth down here, our noble gas core would be xenon. And if we were going to do oxygen and use core notation, our noble gas core would be helium. That's the way core notation works. Okay, let's change colors just for the heck of it. We're going to do chromium and copper. And the reason we're going to do chromium and copper because they're a little bit different. So here is chromium. All right, and let's go ahead and let's take a look at the orbital diagram for chromium just for the valence electrons. All right, so we'll assume that we've got an argon core down here, and we're just going to go straight to the 4s, and then we'll move on over. So let's take a look at that. So for chromium, just in terms of the valence shell, we've got 4s, and you would think we would go ahead and do 4s2, and then we'll count over 1, 2, 3, 4. I know that might be a little hard to see. And we're going to backfill those 3d orbitals. And remember, those d's are at, after you put electrons into that 4s, it moves to a higher energy level. So here come the electrons that we're going to put into 3D. We've got 4 to put in there. And by the way, we have obeyed Hund's rule. These are degenerate orbitals. Each orbital gets its own electron with spin up. These are all indicating spin up. Now notice we've got an empty orbital over here. And we've got a filled 4s, but that 4s is at a higher energy than these 3Ds. So the elements are trying to do with their electrons what everything else in the universe is trying to do, and that's to get to the lowest possible energy. That is what systems do. And so instead of having 4s2 3d4, which is what you would think, this electron that's in this higher energy 4s orbital, this electron that was in the 4s orbital is actually going to move down, drop in to this fifth 3d orbital to give us what we see is a half-filled shell. And what do we know about half-filled shells? They're very, very stable electron configuration. So this half-filled 3D subshell and this half-filled 4s subshell give us a more stable configuration for chromium. This half-filled 4s and half-filled 3D subshell gives us a more stable configuration for chromium than if we had 4s2 3d4. So the electron configuration for chromium using core notation is going to be argon 4s1 3d5. All right, something similar is going to happen with copper. So here's copper, and I can do the same thing with copper that I did with chromium, and that I've got a 4s orbital here. I've got 3d orbitals that are down here at a lower energy level. Once the 4s's are full, the 4s is actually, just think of it as two cats in a bag. It's pretty energetic in there. And then if we look at copper, we've got 9 electrons in the D subshell. So that's going to be, we're going to obey Hund's rule and just have spin up electrons. Now we're obeying the Pauli exclusion principle. 2 electrons in each orbital, 1 spin up, 1 spin down, and we have a half-filled orbital down here. That is, we have an unpaired electron, which is not a particularly stable electron configuration. It has certain properties. And so what's going to happen is the electron that's in this 4s, oh boy, this 4s, let me get my orbital back here, is going to drop in here, spin down. Now I have a filled shell, which we know filled shells are stable. and I have a half-filled 4s. So for copper, the core notation, electron configuration, is going to be 4s1 3d10. And this is the core notation electron configuration for copper. Now, I will tell you that silver will do the same thing that copper will do. It will borrow an electron from its 5s orbital and fill that up. So will gold. But over here with chromium, molybdenum will do it, but tungsten will not. You will really, with respect to these exceptions, only have to worry about chromium and copper as having these particular two exceptions.